So now we'll continue with the Green's function. So remember the main conditions we obtained. Yes.
Okay. When we start discussing on Green's function, we say the eigenvalues must be non-zero to have to make invertible.
Yeah.
Yeah, but
Yeah.
in infinite dimensional space, we do not determine it, right?
In the infinite dimensional case, yeah.
We do not determine it. So how can one show?
Okay, so let me discuss that. Yeah, true. I mean, that argument I gave was kind of intuitive argument rather than being very precise, right? I mean, as you were saying, because in infinite dimensional case. Yeah. So, okay, go ahead.
If the differential operator is invertible, but sometimes it cannot be diagonalized, right? So in such conditions, how can you find the Green functions?
So okay, I mean, so what I will do is I will actually construct the Green's function now. I'll answer both the questions by explicit construction. Though that argument was more intuitive. I mean, it was kind of drawing an analogy with the finite dimensional case because that you have seen, right? But don't take it too seriously, those considerations. I mean, we'll explicitly construct for differential operator the Green's function and show that the necessary condition for that is that there should be no zero eigenvalue. Yeah, we'll explicitly show that. In fact, let me first come to that question anyway. The necessary it's a necessary condition. Okay, so remember, I mean, the few things we had proven already in general, right? Let me see. Some of the statements we proved was that if gxy, the Green's function of the so this was, remember, there were two operators, Lx and the adjoint operator. And we defined this was equal to delta x minus y divided by wx. And this was, we called it little g xy. This was again delta x minus y over wx. So these were the two basic equations. And then from there we deduced several by using the Green's identity. You remember Green's identity was this. Green's identity was that you have v bar Lx u dx w minus other way around dx u bar or u L dagger x v bar w. That's equal to 0. I mean, more generally, it is these boundary terms, q, u, v bar. But by choosing the appropriate boundary conditions for u and v, we set that equal to 0, right? So the Green's identity is when you have already set that equal to 0. If you don't set that equal to 0, that is, by the way, called generalized Green's identity. Okay? But when you have set this equal to 0, then that is the Green's identity. And we basically just use Green's identity and chose various, for v and u, we chose, for the u we chose g, and for v we chose little g. And we found some equations, some conditions that g of yx was equal to g bar of xy. Right? This was just obtained by choosing u equal to, so choosing u equal to g, say x, y, and little g, v equal to little g x y prime. Yeah? And then you deduce from that this equation essentially. I mean, yeah, use as defined definitions and then apply that. Okay, so what it says is that if capital G exists, then small g also exists, right? Because we have an explicit expression for small g. So this in particular implies that if capital G exists, then also little g exists. Okay. In fact, it also shows that if capital G exists, little g also exists and should be unique. Because if there was another, let's say g prime, which is also solving this equation, I could plug that in instead of choosing v equal to g, choose v equal to small g prime, and then you will get the relation small g prime yx equal to g bar capital Xy, right? Also small g equal to the same thing, so small g is equal to small g prime, right? So this all actually gives a very strong relation that if capital G exists and is unique, and vice versa, if small g exists, capital G exists and is unique. So it's all unique. But now let's come back to this question that I mean the question is I mean that was obtained, and that was from the analogy that we made with the finite dimensional case, right? We said the inverse will exist only if the determinant is not 0, and in particular that means eigenvalue, there must be no eigenvalue, 0 eigenvalue, right? But now let's explicitly show that. So so suppose there was a solution Lx u equal to 0. Suppose there exists u such that Lx u equal to 0. Okay, and okay, and now we'll show that capital G cannot exist. Okay, so if capital G existed, small g exists, right? So we'll prove by contradiction. Okay, if capital G exists, then small g exists. So let us use this Green's identity for choose v equal to small g. So v of x equal to small g of xy. Okay, and u to be this particular solution. So u is that solution which satisfies this condition. So and u satisfies this equation. So u is a 0 mode. In fact, let me just call it. Let me put here 0 to indicate it's a 0 mode. So okay, u equal to and u equal to u0. Of course, when we say write this equation, we mean, I mean, if I didn't have to worry about the boundary condition, we know that there are two solutions for this equation, right? But when we make such a statement, it means I can find a solution which satisfies the boundary conditions, right? So it's not, I mean, so okay. So we are saying that there is a solution to this equation where u0 satisfies the appropriate boundary conditions. So such that this thing and u0 satisfies the boundary conditions, whatever the boundary conditions you have chosen. So we choose u equal to u0, and v is this. So let's plug that in this identity. So we find dx v bar. Well, Lx acting on u is 0, so this is 0. So the left hand side is 0. So if I plug that in here, I mean the first term is 0, and the second term gives you you have dx w u, and then u0, and u is u0, and then L dagger x acting on v is delta function, right? V is little g, so that is delta function. So that gives you delta divided by w, so w cancels, and you just get u0 of x delta of x minus y, which is minus uy, right? I mean this is 0, this is minus uy, and that's supposed to be equal to 0. So we u0. So this is equal to 0. So we are saying u0 is 0, right? I mean there is no non-trivial solution. Of course 0 is all, I mean 0 could be a solution if the boundary conditions are also saying Dirichlet boundary condition, right? But what it's saying is that u0 is in fact identically 0. Okay, so there is no non-trivial solution for the homogeneous bound, I mean for the Lx, this equation Lxu. Okay, so again the logic is, so what I did, I assume, let's suppose that u0 existed which satisfies the suitable boundary conditions, right? Then this proves that capital G cannot exist, right? Because we have arrived at a contradiction. We said, okay, let's see if the capital G existed, then small g should exist, but then we apply this in the Green's identity, we conclude that u0 is 0, right? So therefore this is a contradiction. This implies capital G cannot exist. Right? So this is a necessary condition. The necessary condition is that there is no non-trivial solution to the homogeneous, to the equation Lx acting on u0 equal to 0, which satisfies the suitable boundary conditions. the trivial solution is always a solution, right? Because if you use the homogeneous boundary conditions, in fact, in this entire section, we are using homogeneous boundary conditions. So if it is homogeneous boundary condition, and if you choose u equal to 0, that obviously satisfies the equations, right? Not just for Dirichlet, in general. For, yeah. Sorry? Because we said when you substitute this Lx u naught equal to 0, right? Yeah. So that first term is 0. Okay. So now let's continue. Yeah, you had a question. Yeah. This line. I think this was the little gyx was equal to g bar xy, correct? Yeah. I think that we obtained last time, right? I mean, this is equation 8.1. Huh? Sorry? No, we just plug that in here. Just take the Green's identity and plug this in here. I mean, these values, just plug that in here. So this gives you delta function, delta x minus y. Okay. I mean, just plug that in. You see what you find from the first term. You get little g. There's a delta x minus y. Okay. W will cancel. So there's delta x minus y, and you integrate v bar. So x will become y. In this v, x will become y. So x is here. So it becomes y prime. That's the first term. Okay. Second term is Lx dagger v gives you delta function again, right? So this will again, when you integrate the argument inside the u, the argument of x will become y prime. Okay. So you find here, so sorry, this is b bar, sorry, this is bar, this is bar, and whereas there you find capital G, where now x becomes y prime because this is delta x minus y prime. Okay. So this becomes y prime y. That's this side thing, right? So yeah. So now let me proceed with the actual construction of the Green's function. Okay. I mean, what is the procedure to construct the Green's function? Then we'll take some examples, simple examples to construct. Yeah.
I mean, sometimes, for instance, Lx here, our differential operator may be invertible, but may not be diagonalized. Like we can get, this equality may not be true always. The first.
No. So I mean, again, as I said, we will construct explicitly this. I mean, just explicit construction. Then the other issue is, I mean, this is still the Green's function. Then the question arises whether you can construct the eigenvalues and so on. I mean, eigenfunctions and eigenvalues. Okay, that will be, I mean, yeah, in general we cannot say much, but at least for Hermitian operators we can say more, right? Well, we can only say more, but I mean in words, because actual construction will require infinite number of eigenfunctions. That is difficult, right? I mean, for the quantum mechanics problems we have done, there you could explicitly construct. I mean, right? Those are simple examples like harmonic oscillator or hydrogen atom. Those Hamiltonians were easy. I mean, simple enough Hamiltonian that you could construct everything, right? But in general, if you are given some complicated Hamiltonian, it won't be easy to construct. I mean, you use some various methods, perturbation techniques and things like that, no? Which I think you will study more in the next semester, the advanced quantum mechanics course. So there, I think perturbation theory will be discussed. Maybe in one of the examples I will illustrate also how this perturbation theory is used. I mean, how you use the Green's function to construct, to develop a perturbation series. I will try to illustrate that. Okay, so let's go back. And last time we obtained certain conditions on the Green's function. We were looking at a second order differential operator. So we were taking Lx equal to a d2 by dx2. So let me write down here. So Lx of gxy is equal to this. Again, I mean, this is a function of x. Everything is a function of x. G of xy plus b d by dx, g of xy. Actually, let me write everything outside. Plus c, this acting on gxy. That's equal to delta x minus y. So this is our explicit equation, right? I mean, using the explicit form of the Lx. And then we obtained, so what, let me repeat that argument again, because that's a rather important argument. I mean, this is really a generalized function here. I mean, this should be thought of as a generalized function, right? So you should think of this capital G also as a generalized function. I mean, more rigorously. But in fact, what we will see that you can think of Green's function as just an ordinary function. Okay, I mean, as we'll see. Now, the point here to remember is that you remember when we discussed the step function. I mean, step function h, say x minus y. This had the property that, okay, although its derivative is not defined at x equal to y, right? Considered as an ordinary function, it is true. Nevertheless, we know that we discussed that if you think of this as a generalized function, which is called theta x minus y, okay, then the derivative makes sense, right? And furthermore, the derivative dx of theta x minus y is really a delta function. Right? This is what we obtained. Okay, so then we can try to think of it in the following way. Okay, so suppose, I mean, so one derivative of h or theta gives you delta function. Now here you have two derivatives, right? I mean, if suppose I had taken the Green's function itself equal to theta function, that would not work, because the first derivative acting on that already gives you delta function. But then this term has one more derivative, so it will give you derivative of delta function. But the right hand side does not contain any derivative of delta function. Okay, so therefore, what we should have is not that the Green's function behaves like theta function, but the first derivative of the Green's function should behave like theta function. Right? So what we should have is dg by dx. So one thing we conclude is that g itself must be continuous. G of xy must be continuous at x equal to y, right? Because if there was a discontinuity here, already the first derivative would have given you delta function. If there was some, when you take x, if y is here, and as you move along this way or that way, if there's a discontinuity, suppose from here the Green's function comes up to this point, and when you come from here, the Green's function comes like that with some discontinuity. Then in a small region, this behaves like a step function, right? So the derivative would have given you delta function. Okay, so that we cannot have. That must not be the case. So it must be continuous. So both sides, when you come from here and you come from here, it should come to the same point, Green's function, but not the first derivative, because after all, somehow you must get delta function. So the first derivative must have a step function. So we are saying dg by dx must be some number times a step function near x equal to y. Near x equal to y. So this is near x equal to y. Okay, I mean plus regular piece, plus some regular piece. Okay, this is a regular piece. So near x equal to y. Regular meaning continuous piece, but this is the discontinuity. And then we obtained, we just looked at the behavior of the dg by dx as you come from left, I mean, bring the x from the left or from the right to the y, and read out from here what the discontinuity should be, what this alpha must be. Right? And we saw that alpha was equal to 1 over AW. Okay? So the alpha was 1 over AW. A at y, W at y. So we had so that conditions. I mean, this was just obtained by just examining this here. I mean, if you take a second derivative of that, then I mean, this is in general a function of x, right? But when the second derivative hits here, nothing happens. I mean, this is a continuous function. You don't get the delta function from there. Delta function will come when the derivative hits here, right? So you will get alpha times delta function of x minus y. But now I can replace x by y because it's multiplying delta function. So you get the equation alpha y times delta function times a, because a is the coefficient of second derivative, right? So a times alpha is equal to 1 over w, right? So therefore alpha is 1 over a times w. So that's the basic condition. So we get the continuity conditions, the two continuity conditions, continuity or discontinuity condition, continuity and discontinuity conditions. So one is the continuity of the Green's function, which means the g of xy as x goes to y plus meaning coming from the as you come from the right, above y or below y. So this must be equal to g of xy as you approach x from the left by minus. Okay, and the second condition is discontinuity condition. The first derivative, so dg by dx at x, I mean at xy, at x as x going to y plus, minus dg by dx xy as x approaches from the left. That must be equal to 1 over a y wy. Okay. So these are the two basic conditions in the Green's function. Okay. This is just coming from the looking at the this near x equal to y, the behavior near x equal to y. Yeah. Yeah. No, sorry, which is so what I just plugged that in here. And equate the and compare the coefficient of delta function, Dirac delta function on both sides. So the Dirac delta function will come when the derivative hits here. So that gives you alpha times a times delta function. That is equal to and there is no other delta function here, right? The only delta function appears here. The coefficients must match. So that tells you that a times alpha must be equal to 1 over w. No, but this doesn't give you delta function, right? This doesn't give you delta function because g is continuous, right? I mean, this just gives you a step function. D by dx acting on g of xy, g of x y is simply this. So it gives you a step function. So there is a step function there, but also there is a step function here because when the second derivative hits there, that gives you again step function, right? So that must cancel, of course. Yeah. But I'm just looking at the coefficient delta function. That already gives me this condition. So these are the basic conditions there. All right. Now, what else I know about this equation? Well, when x is not equal to y, when x is not equal to y, then of course right hand side is 0, right? Because delta function is 0 when x is not when the argument is not 0. So this is 0, right hand side is 0. So therefore G must be a solution of the homogeneous equation, right? And homogeneous equation, we now choose a fundamental set of homogeneous equation. So first of all, an x equal so G of xy as a function of x must be a solution of the homogeneous equation. Okay. So what I will do is so here is my y. So there is some interval I was calling x0. So x0 to x1, some interval is there, and choose some y somewhere. Now I take so what does it mean? The solution in this region as well as solution in this region, so long as you are away from y. Both of these, both this region and that region, the Green's function must be expressible as linear combinations of the fundamental set of solution. Choose some fundamental set of solution. Say let's call it u1 and u2. So let's say u1 x and u2x are a fundamental set of solution. That means any solution of the homogeneous equation is the linear combination of these two, right? So let's choose here the linear. Suppose that Green's function here is expressible as a linear combination with coefficients c1 and c2. c1 can depend on y plus c2 y u2x, and in this region is some, let's say, some coefficients d1 x d1 y u1x plus d2 y u2x. Let me use the same convention that they have used here. I don't remember, c1 and c2 was for the c1 c2 was for less than, yeah, correct, this is the same convention. Okay, so okay, so we are guaranteed that here it should be linear Green's function should be linear combination of these two, and I just call those coefficients as c1 and c2, which are not functions of x but could be functions of y, right? Because the differential operator is acting only on x, right? So this is, even if it depends on y, it's just a constant as far as this is concerned, right? Same way here is some linear combination, and the coefficients I just call them d1 and d2. Okay. So this is this, yeah.
Why specifically choose x, the region between x0 and x1?
I mean, because I know that from here to here, it's a it satisfies the I mean G satisfies the homogeneous equation, right? Not at x equal to y, but from here to here it satisfies. So here it will be some linear combination, right? Similarly, I know that from here to here, excluding the point y, it again satisfies the homogeneous equation. So it will be some linear combination. At the moment, I'm just keeping it general, completely general, right? Of course, you are saying that why not choose c1 equal to d1 and c2 equal to d2? Okay, if that is allowed by these conditions, fine, right? But it cannot, right? Because if c1 equal to d1 and c2 equal to d2, then we are saying this is just a, throughout the region, it is a solution of the homogeneous equation. But that cannot be, because at x equal to y, this is not. This is in fact it is infinity, right? So for sure you expect already that d1 and d2 cannot be equal to c1 and c2. But at the moment I'm just keeping it general, right? Then we'll plug it in those equations and see what are the possibilities. So now we have 4 unknowns here, right? We have 2 conditions here, right, which will impose some restrictions on some relations between c1, c2 and d1, d2. And then we have 2 boundary conditions also, right? So those are the main things. So we have 4 conditions basically, 2 boundary conditions and that 2 of these continuity, discontinuity conditions, and that will be allow us to fix everything. Okay. So first maybe let's just let's analyze that, since it is written in the blackboard. So I think I can erase this part, right? So this is, so g of xy is g of xy. I'm taking it to be in this region that, and in this region that. Okay. So let's plug it in the first equation. So what we are seeing is that, first equation says c1 y. Now at x equal to y plus, I mean u1 and u2 are continuous functions. Okay. So I don't need to worry about y plus here. I just substitute u1 equal to I mean x equal to y. So u1 y plus c2 y u2 y equal to d1 y u1 y plus d2 y u2 y. Let's do it in the following way. Let's bring it on the other side, everything on the other side. I can collect the coefficient of u1 and u2 separately together. So this equation is the same as This equation is the same as C1. Everything is a function of y, so I will not write down y. In this equation, everything is a function of y. Yeah? So C1 minus C2, C1 minus D1, sorry, C1 minus D1, U1 plus C2 minus D2, U2 equal to 0. This is all at y. Similarly, now let's look at the other second equation. And again, you see dg by dx, so that will just give you, the derivative will only act in the u1 and u2, because that's where the x is right? So you will get again c1 minus d1, again collecting the du1 by dx piece. So du1 by dx, I mean at x equal to y. So this is at x equal to y, plus c2 minus d2 d u2 by dx, why am I right? Partial derivative d by dx, u2 again at x equal to y. That is not equal to 0, it should be equal to 1 over a times w. Again, everything is a function at y. So we have two equations. Now, so we want to determine these guys, I mean these four unknowns here. I mean these combinations. Actually, you only get this combination, C1 minus D1 and C2 minus D2. So these are two unknowns, C1 minus D1 and C2 minus D2. And we have two equations, and we can determine them provided the determinant of this coefficient is not 0. But that is the Wronskian, right? So you see, so we can determine C1 minus D1 combination and C2 minus D2 uniquely, you see, because the determinant of the coefficients u1, u2, du1 by dx and du2 by dx, this is Wronskian w of u1, u2. And that's not equal to 0, right? Because for the fundamental set of solutions, that is not 0. So a solution uniquely exists. Okay. So far, now we have used both of these equations, and we have determined these two combinations, right? But still, we need to determine we need to impose the boundary conditions. Okay. So let's now look at the boundary conditions here. So far what we have concluded that the Green's function g of xy, I can write it in the following way. G of xy equal to, when x is less than y and greater than or equal to x naught, we have, let's write it as, let me define it like this. So you see, so let me write it like this. After all, it was in this region it was c1 y u1x plus c2 y u2x, right? That is what it was in this region. Let me add and subtract this part. So minus d1 y u1x plus d2 y u2x. I have subtracted now, but I must add also d1 y u1x plus d2 y u2x. The reason for doing that is that now you see I can put them together. So you get c1 minus d1 times u1 plus c2 minus d2 times u2. But c1 minus d1 and c2 minus d2 are uniquely determined already, right? So this part is uniquely determined. I mean, it is fixed. I mean, you don't have any more freedom. That's already given. And let me give a name to this. I just call it some gs. I'm just following the same notation. gs of xy. Okay, this is nothing else but that, this whole thing. I mean, the point is that now in this there is no freedom now. I mean, this is completely fixed, right? Because I said these two things are uniquely determined. So therefore, this is fixed. I mean, I have no more freedom there. I cannot play with that. So that plus of course this remaining piece, d1y u1x plus d2y u2x. That is in the region x a to less than y. And in the second, in the region, other region, you have x greater than y and less than or equal to b. There we have simply this, right? Plus d2y, d2x. Where the important point is this is now determined completely. There is no more freedom there. The only freedom is in this part. Okay. So now we look at the boundary conditions. So, so the boundary condition, I mean, as a function of x, it must satisfy the same boundary condition as the boundary condition that u satisfies, right? I mean, Lx acting on the u satisfies certain boundary condition, which I denote by b1 and b2. These are two linear homogeneous boundary conditions, right? So b1 of g, so what we require is b1 of gxy as a function of x. I mean, y is fixed parameter, because this all this differential equation is on the x. So this must be equal to 0, and similarly g of xy equal to 0. This is a shorthand notation for, because remember these boundary conditions were alpha alpha, so this will become alpha g a x y plus beta dg by dx at x equal to a plus gamma. I mean, remember this alpha times the value of the function at one boundary a plus beta times the derivative, the value of the derivative, first derivative at that same boundary, plus gamma times the value of the function at the second boundary, not a, sorry, I should call it x naught. I keep, this is x naught, and that is x1 y plus delta, you know, this same thing, this is the shorthand notation for that. This is just a linear function, right? Dg by dx at x equal to x1. So this is equal to 0, and similarly second equation will be where alpha, beta, gamma, delta are replaced by some other constants, alpha prime, beta prime, gamma prime, delta prime. But so these are a shorthand notations for that. Instead of every time writing these long expressions, this when I write this, it just means that. It's a linear function, homogeneous linear function in the g and the first derivative of g at the two endpoints. So that's what it is. Okay. So this now I can write it. You see, after all, this is a linear function, so I can write. In fact, so even to simplify the notation, let me write also, put it also gs here. I mean, this is 0 plus this. I mean, this is the same as that, right? So let me just, for a shorthand notation again, I write g of xy is equal to simply gs of xy plus d1 u1 plus d2 u2. Okay, where gs of xy is defined as the following. So let me not here, let me put here hat. Okay, this is hat, g hat, where gs of xy is equal to g hat in this region and is equal to 0 in that region. Okay, this is just not to separate it like this. I mean, just to put it in one equation, where it's understood that gs is equal to g hat in this region and equal to 0 in the other region. So just instead of writing, okay. Now just plug that in here and use the fact that this b1 and b2 are linear functions, right? They depend linearly on these quantities. Then I think I can erase this part now, right? I mean, this part is done. I mean, the content of this was simply that these two are determined completely, uniquely. We will, of course, work out some examples. I mean, this is still a general discussion. We'll work out some explicit examples where we will solve these guys. Okay. So that equation I can write, this becomes b1 of gs, gs being that gs. So maybe I should just write this. Gs of xy by definition is equal to g hat xy and 0 in the two regions, x less than y and x greater than y. X naught. I keep mixing up this. This is x naught and that's x1. The reason is I don't want to confuse with the a and b, that's why. x naught and x1. Okay. So this is the definition of GS. So GS of x, B1 of GS plus B1 of D1 U1 plus D2 U2 equal to 0, and similarly B2 of GS plus B2 of D1 U1. Actually, again, I can use the linearity of this. So you get here D1 B1 U1 plus D2 B1 U2. That's equal to 0. And again, by using linearity, D1 B1 B2 U1, sorry, plus D2 B2 U2 equal to 0. So now we want to use this equation to determine D1 and D2. This is fixed because GS is completely fixed. So this is something which is, I mean, there's no arbitrariness here. That is fixed for a given problem. That is fixed. So only unknown quantities are D1 and D2. We have two equations, and you can find a solution provided this determinant does not vanish. Right? So what can I? So okay, here I can erase all this here. So if the determinant of this coefficients of these unknown quantities B1 U1 B1 U2 B2 U1 B2 U2, if this is not equal to 0, then there is a unique solution for D1 D2, right? Okay. If on the other hand, you see, you can ask the question, what would have happened if the determinant was 0? Okay. If the determinant was 0, that exactly means that there is a 0 mode of the LX operator, because if this is 0, okay, so let me just explain that. If this determinant was equal to 0, if this determinant is equal to 0, then it means that there exists a linear combination alpha B1 U1 plus say not this alpha beta, sorry, not running out of the say capital A B1 U1 plus capital B I'm using already, capital C B1 U2 equal to 0, and the capital A B2 U1 plus capital C B2 U2 equal to 0. Then there exists, I mean, what we are saying is that then there exists capital A and capital B, which are non-trivial, I mean, not 0, right? I mean, that just means that if this determinant was 0, this means that these two are linearly dependent. So this is a statement of linear dependence. So there are non-trivial AB that exists which solves this equation simultaneously, right? But that means by linearity again, you see this is the same as, I mean, what is this quantity? This is the same as B1 evaluated for capital A times U1 plus capital C times U2 by linearity, right? So we are saying that if you take the solution capital A times U1 plus capital C times U2, that satisfies the B1 boundary condition as well as the B2 boundary condition, right? So there we have a 0 mode, because the capital A times U1 plus capital C times U2 is a solution of homogeneous equation and satisfies both boundary conditions. So that would be a 0 mode, right? And it's non-trivial A and C, right? As A and C, sorry, A and capital C. So therefore, I mean, it's a non-zero solution also, a non-trivial solution. So determinant equal to 0 would have implied that there is a 0 mode for the LX, right, which satisfies the suitable boundary conditions. Okay. But in that case, we know anyway the Green's function doesn't exist, right? That was a necessary condition. So we'll assume that this determinant is not 0, otherwise there's no solution, we know anyway. So when this is not 0, this is uniquely fixed because D1, D2 is determined uniquely, right? Because you can just write this equation as this matrix acting on the coefficient D1, D2, that is equal to, I mean, take it to the other side, this part, the inhomogeneous piece, right? And then you just take the inverse of this matrix and you get a unique solution for D1 and D2, right? So this means that there exists unique, in this case, unique solution for D1 and D2. And that way you determine completely uniquely the Green's function. Right? So this is the main idea. So I mean, this is completely constructive approach, provided of course if you know the fundamental set. If you know a fundamental set, then this becomes trivial. I mean trivial meaning just a simple algebra. It's not just have to plug in the continuity discontinuity equation and the boundary conditions, and that determines everything. Yeah. Sorry? This is at x equal to y. This is evaluated at x equal to y. Yeah. I mean, the Wronskian was not equal to 0 for any value of x, right? So here we just looked at this Wronskian for at x equal to y. So this is all at y, because in this equation what's appearing is that no, it's no, it's not, it is sorry, b1 of no, not here. No, sorry, no, that was a Wronskian. Is that your question about Wronskian, is it? Yeah. So in the Wronskian, it was evaluated at y, yes? I mean, the Wronskian that we had obtained, you're not talking about this one, but the previous thing which were written down, right? Is that what? You're looking at this C1 minus D1 and C2 minus D2. What? There is no, I mean, here there is no y here, right? I mean, u1 and u2 depends only on x, but now we are evaluating these guys at the endpoints, right? Yeah, here there is no y. In the Wronskian, there was a y. We were evaluating, Wronskian was defined for arbitrary x, right? The determinant u1x, u2x, du1 by dx, du2 by dx at each x. But in that discussion, what appeared was the value of that Wronskian at x equal to y. Right? But Wronskian is not 0 anywhere. Okay. In fact, Wronskian was given by the exponential function, so that was never 0. So, okay. So now let me just maybe this still looks abstract. So let me just work out some examples where differential equation is sufficiently simple that we know u1 and u2 explicitly. Otherwise, it becomes, of course. Otherwise, you cannot do. I mean, you can only do this. I mean, this formal expression, right? Unless you know the u1 and u2, you cannot use this approach, right? So let's consider some examples where u1 and u2 are, I mean, sufficiently simple equation to get the. Yeah. So let's see. In fact, the first. But is there any question before I go to the example? Any other question? Yeah. I'm just using linearity. I mean, what it says, I mean, look at the left-hand side of this equation. That is the same as B1 of A U1 plus B C U2, right? That's the left-hand side. We are saying that's equal to 0. Now look at this equation. Again, this equation is B2 of A U1 plus C U2 equal to 0. Right? Again, using linearity of the B2 condition. Right? But that means that there is a combination which satisfies both the boundary conditions. I mean, this particular combination satisfies both the boundary conditions. And this combination is also a solution of the homogeneous equation. I mean, it is annihilated by Lx, right? So then that means Lx has a 0 mode. Okay, so let's see. So take some example. What's that? Okay. So let's take the simplest example. So suppose I'm looking at just a differential equation d2 u by dx2 equal to f of x. Right? I mean, so this is. Okay, so the corresponding Green's function, and let's take is for simplicity w equal to 1. The weight function is equal to 1. So in this case, it's very simple. A is 1, w is 1, b is 0, c is 0. This is simply, so a is 1, b equal to 0, and c equal to 0. Okay. So the associated Green's function, and let's specify the boundary condition. So let's say the interval is x is in 0 to a, 0 to some number, I don't know. We can even call it, okay, let's say call it a. I mean, this a, this is just a number. I mean, this is just a number. So the interval. And the boundary condition we choose is u of a 0 equal to, so Dirichlet boundary condition. U of a equal to 0. So that's my Dirichlet boundary condition. Okay, so let's look at the, first of all, the homogeneous equation, because remember, to construct the Green's function, you need to look at the homogeneous. So the homogeneous version is simply right hand side is 0, right? Now the solution of this equation, the fundamental set you immediately know, u1 I can choose equal to 1. Clearly, if I plug 1 here, derivative, second, this satisfies the equation, and I can choose u2 equal to x, right? Because the second derivative of x is 0. So this is the two independent solutions. Now look at the, so let's see, first of all, let's check if there is any 0 mode or not. So that means I want to look at, is there any combination of these two which satisfies both these boundary conditions simultaneously? So let's say if I write some alpha u1 plus beta u2, let's consider this. We want this to satisfy both the conditions. Well, that is the same as alpha, let's plug u1 equal to 1 plus beta x, because u2 is x. So this condition already tells me that alpha must be 0, right? Because at x equal to 0, we want this to vanish, but that means alpha equal to 0. And this condition tells me, so alpha is 0 already from the first condition. This equal to 0 means beta times a equal to 0, but that means beta, since a is not 0, right? A is greater than 0, so that means beta is also 0. So there is no 0 mode, right? Because satisfying this boundary condition implies you get a trivial solution, alpha equal to beta equal to 0. So that means Green's function must exist. Okay, so no 0 mode. Yeah, if there is no 0 mode, that means there is no non-trivial 0 mode. I mean, if you had found some solution with alpha and beta not equal to 0, or at least one of them not equal to 0, then that means, what is the conclusion then? That you have a solution for this equation which satisfies this boundary condition, right? That means that so maybe I should mean, what do I mean by 0 mode? 0 mode means something which satisfies the homogeneous differential equation and at the same time satisfies the boundary condition. Okay. So since we say that, we are seeing that there is no non-trivial solution which satisfies this boundary condition, right? That means there is no 0 mode. That's the terminology. I mean, it is to do with the again the same analogy with the finite dimensional case when we looked at. I mean, in general, if I am given a matrix M, and you look at some state V, and you look at the eigenfunction, so it will be this kind of equation, right? So this will be the eigenfunction equation. When lambda is 0, then right hand side is 0, right? So that is like the homogeneous. So think of this operator M as d2 by dx2 and this u as this vector v, right? So this operator acting on the u is equal to 0. That means it is a 0 eigen function. It's an eigen function with 0 eigenvalue. But you have to specify what this u, what vector space it belongs to, right? And what we are saying is this belongs to the vector space which is defined by all the functions which satisfy these boundary conditions. That defines to us not the set of all functions, but a subset of functions. That defines again a vector space because it's a homogeneous boundary condition. So if there exists something which is inside this vector space which satisfies the equation, then that means it has a 0. It corresponds to a 0 eigenvalue. That's why we call it 0 mode. This is very common in the physics literature. That's why I'm using this. Not so much in the mathematics literature. They don't use this word 0 mode, but in physics literature this is very common. So that's why I'm using this. Okay. Sorry. This was the. Where was it? Yeah. Where was I? Okay. So the Green's function must exist. I will later on consider a situation where actually we'll choose a different boundary conditions, okay, such that 0 mode will be there. Okay, we will see. Okay, what we'll do is we'll actually generalize this construction of the Green's function, which will be also applicable when there are 0 modes. Okay, we will do that later. But for the same example, but with different boundary conditions, we'll discuss later. Okay. So now let's see. So let's apply this condition. So whatever the Green's function is, so g of xy. So we can choose this to be so in the say c1 y times u1 is simply 1 plus c2y times x. This is in the region x less than y, okay, greater than 0, and then d1y times u1, which is 1, plus d2y times x in the region where x is greater than y. So this so in the two regions, x less than y and x greater than y. So we choose that. Then the continuity condition, let's look at the continuity condition. It tells me that c1 minus d1 times 1, this is 1, plus c2 minus d2 times x, but x evaluated at y, right? That should be equal to 0. So that tells me that implies that that's one condition. And the second condition is derivative. So when you take the derivative, this y, dg by dx, not y, dg by dx. So this vanishes, and you just get c2 times derivative is simply 1. So c2 minus d2, that's equal to the discontinuity, which is simply 1 over a times w. I mean, a is 1 here, and w is also we have chosen to be 1, so it's simply 1. Right? These are the two. So first equation tells me that c1 minus d1 equal to minus c2 minus d2 times y, and the second equation tells me that c2 minus d2 equal to 1, so c2 equal to d2 plus 1. When you plug it in here, that simply gives you, if you plug c2 minus d2 equal to 1, that gives you minus y. So c2 is equal to d2 plus 1, and c1 is equal to d1 minus y. Correct? That's okay. Now let's look at the boundary conditions. So what the boundary condition says, so this is the boundary condition at x equal to 0. But x equal to 0 is obviously in this region. I mean, notice, so let me draw the picture here. Here is my 0, this is a, that's the lower bound and upper bound, and here is say some y. So we are looking at the boundary condition for the Green's function at x equal to 0. That's the first one, right? First bound. I mean, let me write it as two different equations. This one and then u of a equal to 0. So let's look at the first equation. That is x equal to 0. But x equal to 0 is in this region, right? That means I have to look at this function, because Green's function in this region is given by that, right? So we want to say that, so that boundary condition implies c1 plus c2 at x equal to 0 must be equal to 0. So the first boundary condition says that c1 equal to 0, because at x equal to 0 this vanishes, right? I mean, we are saying that C1 plus C2 times x evaluated at x equal to 0 should be 0. That's the first boundary condition, which means implies that C1 equal to 0. And the second boundary condition is that x equal to a, but x equal to a is in this region, right? It's in this part, in that part. So you get d1 plus d2, so that is d1 plus d2 times x, but x is equal to a, that's the upper boundary. That should be equal to 0 again. Yeah. So that means d1 is equal to minus d2a. Implies d1 is equal to minus d2a. Okay. So now I'm sorry, I use this alpha. I hope this a doesn't confuse with that a. I mean, here a is 1, that a, right? Maybe I should choose something else. I don't know, alpha. I mean, no, but alpha I have used. Capital A. Okay, capital A. Because this can be confusion, you see. So this is capital A, and this is capital A. This is capital A. So these are the equations. So now we determined everything. You see, C1 equal to 0, and look at this equation, that implies D1 equal to y, and D1 equal to y, and that equation tells me that D2 is minus a divided by y. Yes, because once I plug D1 equal to y, so it's minus y divided by a. And then finally this equation, so I have determined C1, D1, D2, and that equation tells me what is C2, and that's minus y by a plus 1, which is the same as a minus y divided by a. C1, I mean just plugging, you have 4 unknowns. So therefore now the Green's function I can write down. So C1 is 0, so this guy goes out, and C2 is simply a minus y divided by a. So you get here a minus y divided by a times x. That is in this region, and in this region d1 is minus d2a. So I mean d1 is y, so this is y, and d2 is minus y by a, so minus y by a x. And now you plug together, combine it together, so you see that it becomes y times a minus x divided by a. It's very symmetric, you see, in the xy. I mean, this is obtained by just exchanging the role of x and y. Right? So yeah. Because I use the fact that C2 minus D2 is equal to 1. You mean this equation here? Yeah. So C2 minus D2 is 1 from here, right? So I plug that in here. So this is just to illustrate, I mean, indeed, from general discussion, we know that all those 4 coefficients, C1, C2, D1, D2, you can determine uniquely, right? If there is no zero mode, right? And indeed, you see in practice how it works. I mean, this is not actually surprising that this is so symmetric, because this operator with this boundary condition actually is Hermitian, in fact. So for Hermitian, you know, gxy must be, there's a symmetry. See? So that's why this happened. Okay. Now let me consider a slightly more complicated example, and maybe that will also illustrate to you how to develop a perturbation theory. I mean, there is an example 2 which is given here. I will not discuss example 2 because really it doesn't shed too much more light than what we had done in general case. That's example 2. It's a, I mean, it's not, it doesn't shed any more light. It's just the same. You have to assume the existence of a fundamental set of solutions and then proceed as far as you can do. It's just the second thing is done just for the case where you have chosen the weight function. Remember, given any second order operator, you can choose a weight function such that it becomes self-adjoint, right? So they have done that for that choice of the W, which makes that self-adjoint. But I don't think it sheds too much more light than that. Okay, so now let me consider another equation. This is before erasing, any other question here? Yeah, so I mean, yeah, so the Green's function now can be used to construct a solution of this inhomogeneous equation, right? Because this solution of this equation is simply u of x is equal to dy capital Gxy fy from whatever the range is 0 to capital A. Weight function is 1 because that's one. So this will be solve this equation, general equation. For any f, you just have to plug this g and integrate it. Of course, this equation is already very simple. I mean, but this is more to show that how this works. That all these 4 coefficients can be fixed uniquely. Yeah, then I mean, as I said, in all of these things, when I'm using this method, I need to know the u1 and u2, right? I mean, in this case, u1 and u2 are simply 1 and x, right? Once you know u1 and u2, you can just proceed. u1 and u2 are the fundamental set of solution. If you know the fundamental set of solution, you can just proceed with this procedure and explicitly determine the Green's function in terms of u1 and u2. Right? I mean, this we already did in the previously. In the general discussion, but now in these examples I'm taking, it's just that they are simple enough so that we know u1 and u2 explicitly. If you don't know u1 and u2, this is not very useful. Yeah. I mean, this means basically if you don't know u1, I mean one of them, because other guy you can determine from the one, right? So. Okay, now let me consider a slightly more complicated example where we don't know u1 and u2 actually. I mean, at least it's not written in a simple form. Equation is this: x square d2u by dx2 plus x du by dx minus 1 minus nu square x square acting on u equal to 0. So this is my Lx. Now this is very complicated. I mean, it's not. You cannot find u1 and u2 in a simple way because of the presence of nu. If nu was 0, then it's trivial to find the solutions of the equation. So first, let me set nu equal to 0. So first, let me set nu equal to 0. Then you see what is the property of this equation. Sorry, there is a u already. So u I should put inside here. I put already u there. Okay. Now the property of this equation, you see, suppose u was some polynomial. I mean, say x to the power of alpha. Let's say. Suppose u was equal to x to the alpha. Then when you take two derivatives on x, it's going to reduce the power by 2, right? But then you're multiplying by x square. So you get back x square power. I mean, original power of x. Here again the same behavior. This will reduce the power by 1, but you're multiplying, right? And this term is just simply 1. So you see that a solution of this equation, if nu was equal to, so let me first take the nu equal to 0 case. So in nu equal to 0 case, it becomes very simple because you can just take the answer, it's u equal to x to the power of alpha, right? And then just plug that in here. From the first term you get alpha times alpha minus 1 times x to the alpha. Everything is coming with x to the alpha. That's because this reduces the power by 2, but then you're multiplying by 2, power of 2. Whereas this guy, so x to the alpha I can take out as a common factor, plus this will give you alpha from here, and this minus 1 just gives you minus 1, right? And that should be equal to 0. A very simple equation, right? So you can see that this is the same as alpha minus 1 times alpha plus 1, this combination. So the two solutions are alpha equal to plus 1 and alpha equal to minus 1. So you can choose, say, u1 equal to x and u2 equal to 1 over x. So unfortunately, if nu is there, you cannot do this, right? Because this is not going to work, because this will, as I said, all of this will stay as x to the alpha eventually, right? But that will become x to the alpha plus 2, right? So in that case, you will get actually a power series solution. And these are the things we will discuss in after this next part of this chapter. After the Green's function, the next thing is the series solutions. So there will be power series solutions. We will discuss that. But for the moment, let's see how we can at least think about some kind of a perturbation theory. So idea would be the following. Okay, suppose nu is not a 0, but nu is something very, very small. Okay, then let's take it on the other side. So what we are seeing is that this must be this times u equal to, so minus minus plus, so minus nu square x square u. Okay. Now if nu is very small, you might imagine to treat it as a perturbation. Now you try to write u equal to some the solution when let me call it u naught. Sorry, this is not 0 mode. It's not 0 mode. Just u naught. U naught is a solution with nu equal to 0. That is this linear combination of these two. Plus something which goes like nu square times u1 plus nu to the 4 u2 and so on and so forth. If nu is small, you might try to imagine making so these are functions of x. These are functions of x. But you might try to imagine making such a series expansion in nu. If nu is very small, you might say that if nu is 0, then of course all this is already gives a solution. But if nu is very, very, very small, maybe this is a pretty good approximation. No? And so on. So if you want to be more precise, you go to the next order and so on. So now you can do the following. So u naught I've already found. Okay, I mean I have to subject to the boundary conditions and so on. But for the moment, let me ignore boundary conditions. So I already found u naught is some linear combination of these two. Okay. Then I want to determine u1. So I mean when I plug this in here, so what's going to happen? This term. So look, this differential operator acting on that is 0. So let's plug that in. So when I apply this, this is called, I mean, let me keep it outside. So this is my Lx, right? So Lx acting on u is Lx acting on u naught plus nu square times Lx acting on u1 plus nu to the 4, Lx acting on u2 and so on, right? That's the left hand side. Now right hand side is minus nu square x square u naught plus nu square u1 plus nu to the 4 u2 etc. Okay. Now you see, now let's just equate the powers of nu on both sides, right? Coefficients of the same power of nu. Well, first term is 0. I mean there is no nu to the 0 term here. Here there is a nu to the 0 term, but by definition we have chosen u naught to satisfy the Lx homogeneous solution. So this vanishes. And then you have the equation nu square times Lx u1 is equal to minus nu square x square times u naught. This is the nu square order, right? So the nu square order, you see Lx u1 equal to minus x square u naught, right? Now u naught you already know, it's the particular linear combination of that. You plug that in here, then this becomes an inhomogeneous solution equation for u1, inhomogeneous equation. But if you know the Green's function, where the right hand side is known function, right? Because u naught you already know. Sorry, this is x square. So this you already know. So then you can use the Green's function to compute u1, if you can construct the Green's function, right? Then you know the u1. Now let's go to nu to the 4 order. Nu to the 4 order, you get Lx u2 is equal to x minus x square. What is that? Nu square. So nu square nu to the 4. So minus x square u1. So now that you know U1 already, you can plug it in that. It becomes an inhomogeneous equation for U2. You can determine U2. So you can, to whatever accuracy you want, you can keep going in principle. This is what is called perturbation theory, right? So this is a perturbation theory nu. Nu is a parameter in this equation, and if nu is small, this would be pretty good approximation. I mean, already the first couple of terms will give you a very good approximation. If nu is large, you cannot apply this method. So this is the perturbation theory. I don't know if George has ever told you about perturbation theory. No, in the advanced quantum mechanics you'll see. Because most of the realistic Hamiltonians will not be so simple. I mean, like the harmonic oscillator or hydrogen atom. No, it will be much more complicated.
I mean, when there is electromagnetic radiation, then we need some approximation. Yeah, but we didn't go to detail.
Yeah. In fact, actually, we only know what to do perturbation theory in the real problems. In the real problems like standard model problem, I mean, all of these things, the Hamiltonian is too complicated. So what we do is just try to make a perturbation theory expansion, and that is not always valid because we know that in certain dynamical systems, this perturbation, this is called coupling constant, let's say. This coupling constant is very, very large. So in that case, it breaks down, and then that becomes very difficult to analyze. Okay, but that's a problem. Okay, so let's see now. Let's just we want to construct the Green's function for this. I mean, this was just a motivation. Now you can just forget about it. You can just forget about all of that, and we are looking at the Green's function for this equation, for this. Where we know this. Where we know the fundamental solutions already, and let's consider some Green's function. Let me use the same, although it's not necessary, but let's use the same boundary conditions. Yeah, so the boundary conditions are, so x is in say 0 and 1, and we take a Dirichlet boundary condition, u of 0 equal to 0 and u of 1 equal to 0. So Dirichlet boundary condition again. Okay, just to construct the Green's function. So let's see. So again, we write the g of xy equal to c1 u1. So c1y times x plus c2y times 1 over x. That is in the region between x 0 up to y, less than y. And here you get d1y x plus d2y 1 over x greater than y 1. Okay. So again, let's look at the continuity equation. So you get continuity equation tells me that c1 minus d1 at x times x plus c2 minus d2 divided by x, that should be equal to 0, one equation. And then the derivative, so you get here c1 minus d1, derivative of x is 1, so that's that, plus c2 minus d2 times derivative of this gives you minus 1 over x square, but x has to be substituted y. So actually here also, this is y, that's y. That is equal to, let's see what is the weight function. It's not written here, but I suppose the weight function is just 1. I think the weight function is this 1 because it's not specified here. So 1 over a times w, a is x squared, so it's 1 over x squared. X 1 over y square. X has to be substituted as y. So so this equation tells me that c2 minus d2 equal to minus c1 minus d1 times y square. And this equation tells me, you substitute that. So C2 minus D2 is minus C1 minus D1 times y square cancels. So it becomes 2 times C1 minus D1 equal to 1 over y square. Yeah, I just substituted that, and I'm just, yeah. So this minus becomes plus, y square cancels, and these two add up to give you a factor of 2. So C1 minus D1 is this divided by 2y square. And therefore, C2 minus D2 is y square cancels, so it's simply minus half. Okay. So that's the condition. Now let's look at the boundary conditions. For this one, x equal to 0 is obviously in this region. So what we are seeing is that at x equal to 0, this must be 0. That tells me that C2 must be 0. So this condition implies C2 must be 0. Right? And then at x equal to 1, so that is in this region. So you get here D1 times x equal to 1, so D1 plus D2, again 1 over x is also 1, so that should be equal to 0. So these are the conditions. So now we can, I think, solve everything. Let's see. C2 equal to 0 implies from there D2 is half, correct? D2 is half. And then if D2 is half here, this implies that D1 is minus half. And then substitute there. So substitute there to determine C1. So if this is minus half, minus plus half, you take it on the other side. So C1 is did I minus plus? Yeah, 2C2. So what do we find if I substitute? 1 over 2, 1 over y square, minus 1, minus plus, so minus 1, yeah. So that becomes y square minus 1 divided by y square. No, other way around. Yeah, 1 minus y square, sorry. 1 minus y square divided by y square. So that's it. That is the Green's function for this particular boundary condition. If you choose different boundary conditions, you will get different forms of the Green's function. I don't know if this is the right one. So C2 is 0, C1 is, so that means substituting that you get here 1/2, 1 minus y square over y square times x, and that is 0. C2 is 0. D2 is half, and D1 is minus half. So this is half, and that's minus half. So you get here, maybe I made a mistake somewhere. I think I made a mistake somewhere. There is a y, there is an extra y. I'm not sure, you see, I'm not sure if the weight function is 1.
C1 minus D1 over y squared plus 1.
Yeah, sorry?
C1 minus D1 1 over y squared plus 1.
I know. So what happened? C1 minus D1. Well, C1 minus D1 already from here I see is. I think I made a mistake. No, I'm not even sure whether the weight function is 1 here. Okay, I don't know. I mean, what the weight function here is, but there is it. Okay, let's see. Let's start from here. So this equation tells me C2 minus D2 is C1 minus D1 times y square, right? Minus C1 times D1 times y square. And this equation is telling me C1 minus D1. And is that 1 over y square? Is it 1 over y square or 1 over y?
1 over y squared because a is x squared.
A is x square, correct, correct. So it could be that I think they have chosen the weight function as 1 over x maybe, yeah. I have a feeling that maybe they have chosen they have not specified the weight function here, unfortunately. In this I am looking at the page 282. Page 282, example 3. Page 282. Because otherwise I don't see any 1 over.
That's C1 minus D1 and not 1 over 2y squared.
So let's see. So I substitute C2 minus D2 here. So this minus minus is plus. C1 and y square cancels.
Yeah, 1.
So and this adds up. So twice C1 minus D1 equal to 1 over y square. So this is twice C1. So 1 over 2y square, right? But I have a feeling that it's not. I think there is I think they have taken the weight function. Maybe the weight is not equal to 1, but 1 over x. So that W times A will be x. I have a suspicion that because they are referring to this equation, see that's the point. They are referring to the consider the right side 9.32. No, with the result of example 2. But in example 2, as I said, they are precisely looking at the weight function, which makes this operator self-adjoint, right? So probably it is not the 1 over x. I mean, it's not W equal to 1, which makes it self-adjoint. Is it written there? Ah, I didn't see. Okay. Okay. Good. So then W of x is 1 over x. Okay, that's the. But it doesn't matter. You see, I mean, they have done it only for the W which makes this operator self-adjoint. But you can also do it for 1. It doesn't matter, I mean, for this discussion. So what I have done here is for W equal to 1. But if you want to do that for W equal to 1 over x, then this becomes y. So that becomes 1 over 2y. And then when you substitute this here, so one factor of y cancels, but the remaining y remains. So this is the same as minus y by 2. Okay. And okay, here of course the weight function doesn't enter. So this part is still the same. This part doesn't change. Right.
Why equation by equation omega equal 1 and a equal e square, but x equal y. We must find.
No. So what I did before was for W equal to 1, right? There's nothing wrong with that. No, this is the Lx. Lx is not. I mean, I have to specify W. What is W, right?
The second condition did that x equal y and equal 1 over a multiplied omega.
So which equation are you looking at? This one. This one.
Yes, equal 1 over a dot omega.
Yeah, but a dot W we said is x. So see, what I did before was W equal to 1. Then what I did before was correct. Now I'm saying that suppose you want to take W equal to 1 over x. What things will change? Okay. They have worked out for W equal to 1 over x. So I just wanted to check whether we get the same answer as them. In this example 3, they have chosen W equal to 1 over x. What I did before was W equal to 1, which is fine. I mean, that's okay, nothing wrong with that. But now I'm just trying to do for W equal to 1 over x, in which case WA is equal to x, so that's that. And now if you substitute C2 equal to 0, that means D2 is equal to, if C2 is equal to 0, D2 is y by 2, yes, D2 is y by 2, and D1 plus D2 equal to 0 means D1 is minus y by 2, and then if you substitute in that equation, so C1 is equal to D1 over 2y plus D1, which is minus y by 2, which means 1/2 1 over 2y times 1 minus y square. Yeah, correct. That is the thing. So now let's go back here. And so C1 C1 is that. So you get here 1 over 2y times 1 minus y square times x, because C2 is 0. And D1 is minus y by 2 times x, and D2 is plus y by 2 times 1 over x, which is the same as 1 over 2x times y, 1 minus x squared. You see, again, there is a symmetry between x and y. That's the reason. Before the expression we were getting, it was not symmetric in x, y exchange. That was because w equal to 1, this operator was not self-adjoint for w equal to 1. But for w equal to 1 over x, it's self-adjoint. So that's the only difference. And that's why you get the same. But the previous thing was also okay, so long as if you don't have to be self-adjoint, no, it's okay. Okay, so I think, yeah, so maybe, have I already finished the time? No, yeah, 11:45. Ah.